Great, thank you. So hopefully I get extra time. But anyway, very good. So this is some work that has been in progress for a while now with the following set of wonderful people. And I also want to point out to some work we did with some students in Southampton and Radu, who's in the audience somewhere. Excellent. Very good. So let me start with some very brief motivation about why we care about observables. I'm sure everybody knows all of this. As all of you know, scattering is one of the simplest processes that you can do in a quantum field theory or quantum gravity. And what it allows you to do is it allows you to quantify certain observables in flat space. Yeah. One such example that we all learn when we compute or when we ever take a quantum field theory course is something called scattering amplitudes. All right. And scattering amplitudes are not only interesting because you can compute them, but they're also interesting because they're related to physical experiments for which you often need to measure something called a scattering cross-section. Now, the first example of a scattering cross-section that we come across is when we compute an S matrix and we square the S matrix. Okay, so we first compute something like an S matrix, which is an in-out correlation function using Feynman path integrals. And then what we get out of it to actually measure things is what's called an in-in correlation function, because it looks like a correlation function between two in states. All right. And usually any set of observables that you like are computed using such in-in correlation functions. And the way we do it in practice is to first compute the scattering amplitude using something called Feynman diagram. And we typically work in momentum space. Position space is wrong. Typically work in momentum space, but working with amplitudes is not very easy beyond your first course in QFT, because you encounter things like off-shell particles, you encounter things like spurious poles, and often when you try to simplify amplitudes, for anyone who's ever tried to compute a 6-point amplitude in Young-Mills, you already know this, it can involve very heavy algebra. And in fact, this is not new. All of this was much. I mean, it was very well known that it can involve super tedious algebra, but the final answers look super nice. And as far as I know, the first example where this was seen was when people computed the 2-to-2 graviton scattering. It's not people, just one person did it. He did this in 1967. And he had this quote in his paper, where he sort of advocated that there might be an easier way to compute it, because he did a lot of algebra and found the answer was super simple. And there was a similar quote, which is perhaps much more well known by Park and Taylor in their paper in 1980s. Eventually, we found the easier method. It took some time, but we eventually got there. And now we have a very well-developed amplitudes program where many people work on, and it's super interesting. So the take-home message for this talk would be, is there anything analogous to some simplification like this in cosmology? And what I'll tell you is the answer is yes, which is why I'm giving the talk. And the one take-home message will be that the final answers are often easier than building blocks. So we spend a lot of time in thinking about the building blocks, but the final answers can be super simple. And sometimes this needs a new way of thinking about them. And you may need to make some special choices for your masses or your helicities, but eventually you'd want to you'd want to get rid of those choices. Very good. So just an outline of the motivation for today's talk says, what are the kinds of in-in correlation functions we can compute in curve space? And how do we compute them directly without relying on these building blocks? And one such example that I'll work on with today is really the simplest example you could think of in quantum mechanics, which is just an expectation value. And it has a name, it's called equal time in-in correlation functions, because they're simply operators which are inserted on a given time slice at various spatial points. And in FRW universe, these are often called cosmological correlation functions. People say they're related to experiments, but as far as I know, it's not beyond 2 points as of now. So we should wait more for experiments. But even if you were not interested from cosmology at all, you might just be a person who's interested in doing out-of-time ordered correlation functions in condensed matter physics. And then you would encounter something called Schwinger-Keldysh path integrals, which also have a very rich history and are related to these things. But even if you didn't care about that, and if you're a person doing ADS-CFT, you might still be interested in this problem because these wave functions that appear in this thing are related to ADS partition functions, as I'll mention soon. Good. So let me just state the result in case you want to fall asleep after this. It's right after lunch. So what I'll tell you about is just like there was a simplicity that was seen for scattering amplitudes in flat space for spinning theories. In cosmology, you already encounter some simplicity like that for scalar theories, and I'll be very precise what I mean in the next few slides. And the final result, that at least one of the final results that I'll try to convince you of, is that this cosmological correlator you can think of as an integral of Feynman diagrams in flat space. Okay, good. And I'll mention how these things can shed light on the structure of loop integrals, which is what this complicated word means, and also how you can use this to derive some consistency relations between these objects. Very excellent. So just to set conventions, I'll be working in something called the Poincare patch in Disato 4. It has a metric of this kind. It's almost like your flat spacetime with this pesky factor of square root g. And I'll be evaluating these correlators on this given time slice. And I'll be working in something called momentum space. And what I mean by momentum is simply the three-dimensional Fourier transform along which I still have translational invariance. Okay. And I'll also butcher the word energy, and I'll call this object the energy, which is the square of 3 momentum. Very good. Excellent. So the first time we learned quantum mechanics, we encountered this expectation value, which is the inner correlation function. And you can actually think of this as a path integral, because we all like doing path integrals. And this particular object can be thought of as a path integral in the field space in the following form. You just insert your probability density, which is mod psi square, and you insert your field operators. Good. Now, before doing this path integral, we need to address what the state psi is. And the most common choice, or the simplest thing to even study, is what's called the Bunch-Davies vacuum. And it can be constructed by one more path integral. And that's just a fancy way of saying that this state satisfies the Schrodinger equation. Okay. So what this roughly means is that at early times you have nothing, which is indicated by 0. And at your t equal to 0, the time at which you want to compute your correlation functions, it has some profile phi. And for those of you who have done ADS CFT, you would recognize this path integral as the same one you use for computing ADS partition functions. Although for my talk, that's not going to be important.
So I guess the last statement is for empty partition.
Sorry?
That was for adding insertions to this last statement.
Yes, it does, but it's not going to be relevant. I'll exactly mention what I mean when I say it's related to ADS in a couple of slides. Right. Very good. So just to give you an example for what this path integral computes for you, if you were to do this for a harmonic oscillator, you would use the Hamiltonian of this kind, and as you all know, the ground state of a harmonic oscillator is the Gaussian, which looks like this. You could repeat this for a free field, a free scalar field. You have a slightly more complicated Hamiltonian, but then your ground state still looks like a Gaussian, but now you have to integrate over the energy modes. All right. Of course, this was so simple because it was the free theory. But in general, when you're not doing free theories, you can, instead of this, you'll have some longer expression, which generically looks like this. But for the free theory, the only term that would survive is this guy, okay, which is basically the spectrum. And these objects are called wave function coefficients in this language. And if you were to compute ADS correlation functions by analytic continuation, you could compute these objects. Very good. Excellent. Now, just like we have Feynman diagrams when you compute scattering amplitudes, you have things called Witten diagrams when you compute these objects. And the only difference with Feynman diagrams here is that you now have a special time when you're computing things at. So your propagators can end at that time, which is a new kind of a propagator, the things you usually strip off when you're doing amplitudes. And these are called bulk-to-boundary propagators. And the other ones are the bulk-to-bulk ones. So for instance, if you were looking at the 4-point wave function coefficient in phi-4 theory, you would draw a diagram like this with 4 points ending on the boundary and phi-4 being this guy. Similarly for phi-3. And whenever I draw such diagrams, my momentum conservation is only along the spatial direction, which is the thick line. Good. So just to give you a feel for how these things look like, even for a super simple case, let me consider what's called a conformally coupled scalar field. They're not very different from massless fields in flat space. And the propagators for these guys look almost like the ones you see in flat space. For instance, the bulk to boundary propagator looks like a plane wave. And the bulk to bulk propagator has one additional term apart from your standard time ordered Feynman propagator because it has to satisfy some boundary conditions. But modulo that, it's very similar. Now, what happens when you actually try to use these to compute diagrams is that instead of getting integrals on time, which go from -infinity to +infinity, you now get integrals which are cut off at the time you want to compute your wave function. So you would have gotten an integral like this if you want to compute, say, the 4-point function of I4 here. So there is a part that gives you your standard spatial momentum conservation. But instead of getting the energy conservation, you now get a pole because this integral is cut off at t equal to 0. And this is a generic feature whenever you try to do any calculation of this kind, that instead of getting delta functions, you get poles. These poles have very interesting physical meanings, which I'm happy to talk about later on. Good. If you try and do this for a higher point function, let's say when you have an exchange graph, you now also have a bulk-to-bulk propagator. For this theory, you end up getting rational answers. And you can also write down some very nice recursive formulas, especially if you're these three authors, you would stare at this answer and notice, wow, that looks like a product of two lower point functions. It's not BCFW, but it's still sort of nice because it's diagrammatic. And it has some nice generalizations for higher spin. But that's not all. The reason people are scared of the subject is because if I took a slightly different theory, for instance, if I took phi cube theory, and I compute a very similar exchange diagram, because of these time integrals being more complicated, already at tree level, I start getting dilogarithms, which is not a feature you have in flat space, because in flat space, the first time you would encounter any object of this kind is if you computed a one-loop diagram. Okay. Things make the subject untractable. Good. Excellent. But notice this was still the wave function coefficient. Yeah. All these propagators and everything I used was to compute the wave function coefficient, because once I have the wave function coefficient, I have to further do this one more path integral. So in this case, if I were to compute this 4-point function, 4-point correlation function, I expand the wave function coefficient in terms of pulling the Gaussian factor outside, along with the perturbations. And I would find that in this 4-point function, I receive a contribution from the 4-point wave function coefficient and product of two lower point wave functions. So in this case, you get a product by just thinking about wave contractions. That gives you this new term. This was too simple, right? If you were to generalize this for higher points or higher loops, this expression soon gets more complicated, and you have to sum over all these guys. And when I use the word building blocks at the very beginning, these are the things I referred to. The stuff you get from naive width and diagram computations are what I'm calling building blocks. And you have to really sum them over and get the final inning correlator. And when we did this computation 3 years ago, we got surprised because this final sum was much simpler than what we initially expected. Excellent. Now, to see the simplicity, you have to play one trick. The one trick is, one of the few tricks we know what to play with. In this case, it's the Fourier. It's going to some analog of Fourier space. Okay. So, for instance, let's consider this exchange diagram when we still got a rational answer. So this guy is the same guy which gave me this. It's some rational answer. And instead of working with the form of bulk-to-bulk propagator, where I expand it in terms of, my time-ordered function, which is like the Bessel functions and so on, I instead work with a representation which simply looks like this, which almost looks like your standard Fourier transform of the propagator, except that it now has signs instead of exponentials. And it has signs because it has to satisfy a particular boundary condition. But now if you take this guy, and you simply switch the order of integrals, you simply perform your time integrals first, then what you notice is that your answer looks like some rational function outside times the exchange diagram in flat space, which is 1 over p squared in this case. Good. Now, this is some reason to be excited, but it's not quite, because if you try to extend this for one loop and so on, it's not easy to read these factors off by just looking at the graph. You can always, in principle, do this, but it gets very complicated very soon. But when we tried playing this trick for the NN correlator, we were surprised. Because turns out this guy, the NN correlator, can also be written as an energy integral over the flat space exchange, except with a tiny difference in the numerator. But what we were even more surprised with is that this kind of function works for arbitrary points and loops. Okay. Difficult, I'm just turning around. Anyway, so for instance, if you were to work at one loop, I have 5 minutes left. Wow, okay. So for instance, if you were to work at one loop, you would get an integral over the flat space bubble diagram with a very similar looking factor outside. But it's a factor that you have to work out once for your theory. And once you've worked it out for some simple graph, it just generalizes to higher graph. Now, a point of caution here, sometimes this integral transform is confused with something like a celestial transform. But the point is this integral transform changes if you change your channel. You know, when you compute things like celestial transforms, for those of you who have seen that, you take your scattering amplitude in flat space and you compute the full, you compute a Mellin transform of that full object. But here you have to change your kernel depending on your particular channel. You have to do some permutations here, but anyway. Of course, this is too abstract now. A much more clean and diagrammatic way is the following. For instance, if I were to just take the expression in the previous slide, which was for the one loop bubble, I take my flat space bubble graph, which is this integral, the 4-dimensional integral here, which is represented by the black lines. And I add to that these two propagators coming out of the external vertex. There's a reason I call them propagators, so ask me later. But anyway, and these propagators look like this. And you can just generalize this diagrammatic rule to anything. And that magically would compute for you this guy. I mean, it's not magic. There's a good reason, but anyway. Excellent. Now, of course, what I told you looked too simple. And why was it so simple? Because I chose a particular theory. If I had 1 more hour, I would talk about how these propagators change depending on when you add masses to your system. If you were to look at phi-cube interaction, for which we got that scary looking dilogarithm, already these propagators become slightly more complicated. There's also some additional issue when you try to do gauge theories and gravity. You have to take care of some residual gauge invariance. But modulo all of that subtleties, things do work out. Good. Now let me tell you some practical simplicities of having this. For instance, if you look at this one loop bubble graph, which we can get by this following integral, you can think of this as summing over these building blocks that I mentioned before. Yeah. So each of these building blocks is a Witten diagram. For instance, psi 4,2 here looks like your one loop bubble in ADS, or if you like this diagram. And if you perform the loop integral here, you would just get a dilogarithm. Fine. I mean, the exact structure here is not important. You just get a dilog. But what's nice is if you take the dilogs from all the 3 terms and you add them, you instead get a logarithm for the final answer. Okay. And for this particular case, it's super easy to see why it happens if you have this integral representation. It's simply because of the fact that you're integrating a logarithm with some rational functions in front with -infinity to +infinity as your limits. And this is what I meant when I said there's a transcendentality drop. So initially you start with functions that have dilogarithms in your wave function coefficients. De Sitter correlator looks like logarithm. Again, there's a very simple counter-integral argument why it happens. If this time, I'll talk about that later on. So how much time have I got exactly? 3 minutes? 2 minutes? Okay, thank you. Approximately 4 minutes. So very nice. So there's also another way to see this the simplicity, which is you could wonder that, oh well, look, you introduce these distractions which look like your p variable, which never really existed initially, and also some L0 variable which has no meaning. So you could think of integrating those out and be left with something which only keeps your 3-dimensional loop integral. And then you can ask, what happens if I compare the integrand of my correlation function and the wave function when I look at the particular loop integrand? And you notice something, or if you leave, you notice something. that this guy has a pole which looks like 1 over L, where L is mod of your three-dimensional loop integrand, and your wave function has a pole that looks like 1 over E total plus L. It nicely looks, it's super similar, right? But the moment you actually try to do this integral in 3 dimensions, you then see that this guy is the reason you get something of high transcendentality, because now with a d cube L on top, the pole at 1 over L is not really a physical pole. There's really no singularity at L goes to 0. And hence these guys are, if you like, these are polynomials, whereas this is a log, and then you get dilog, log, blah, blah, blah. There's also something interesting for the triangle diagram, but I'll not have time to talk about that. Very good. Now there's one more thing that you can do whenever you see Feynman diagrams. You can set propagators on shell. Yeah. It comes up at some chapter in Pascal and Schroeder when you hear about optical theorems. But in here, what it means is to simply cut propagators. And this is work in progress with, in fact, one person in the audience, Sadra. And you can cut propagators and set things on shell. And these are, you can play this very similar game of, Katkowski rules and sequential discontinuities and all the stuff you like in scattering amplitudes for this thing. But for the purpose of these next 1 minute, I'll just talk about something super simple, which is what happens if I cut the propagators I introduced on top of flat space propagators. Yeah. So I started with some integral expression that I had a flat space bubble graph with some extra propagators on top. So what happens if I set them on shells, if I just cut them? And turns out what ends up happening is that you recover your flat space Feynman graph with some energy conserving delta function that you would expect. Thanks. 30 seconds. Excellent. And then you can get further relations once you start relating a cut to a discontinuity. So for instance, one particular relation which I like very much is to say that if you start relating these cuts to discontinuities, that by discontinuity I simply mean stuff like this, you end up getting very non-trivial consistency conditions between these or for these coordination functions. Okay, and what's even nicer is that some of these seem to generalize to arbitrary mass. So we started looking at things which have very specific mass, and we are now able to, hopefully, when this comes out at some point in 2 years, we can remove that particular constraint. Very good. There's some story for the wave function, but I have minus 30 seconds. So let me just conclude. So for the last 30 minutes or 20 minutes, I told you about this new integral representation for computing in correlation functions in de Sitter space by writing them as energy integrals of flat space scattering amplitudes, which are things we know well. So we have to do one more integral on top of that. So this brings us new connections between cosmological graphs and amplitude, and hence explains the title. I didn't tell you why this happens, which is sort of an interesting question. Integral representations, you can get many non-trivial constraints, which is basically what I tried to say. There are some future directions, but thank you.
Yeah, so in flat space, in flat space, when you take sequential discontinuity, you have to be careful about the domain when you take this. Like
you also have to be careful, yeah.
Yeah, so you're taking a particular monodromy contour.
Absolutely. So this is just an examples which we, the issue in this business is there are very, very, very few integrals that you can actually do and test what you're doing. So the ones we are doing, indeed, we are doing exactly as you said. We are picking a particular monodromy contour, and it turns out they just work easily for any other choice you could have made for these simple examples. But for more complicated examples, you're completely correct.
Okay, thank you.
Questions?
You touched more about the reducing the transcendentality.
Yes.
And how it's related to the contour.
Sorry?
And how it's related to the contour that you showed.
Very good, very good. So for this particular case, the point is that am I still audible to you? Okay, very good. So the point is, here the integral that you get from while trying to perform this energy integral over the bubble diagram something that looks like a logarithm with some rational function in front. Now, what saves you? Now, normally, if you just look at this integral, if you were an amplitudes person, you would have said that's a dialog, because you're integrating log with some rational function in front. But what saves you are these limits. So what happens is when you have these limits from -infinity to +infinity, you do something which you do in undergrad, which is to take a residue at this point, which is from this pole, along with the discontinuity across the log. The point is the discontinuity across the log is simply pi. And so this semi-definite integral is now again a log. So the transcendentality doesn't change for these cases. You would be in trouble if you had square roots, but you start encountering them when you have boxes.
Okay, now let's thank Chandramouli.
I have a question. At several points in your talk, you mentioned that you'd get these results from analytic continuation from ADS.
Yeah.
But is that so simple? I mean, this is quite different.
For the particular masses I'm working with, it is because it's just conformally coupled or massless scalars or conformally coupled indices. It's almost like flat space with interaction. Even for massless scalars, it's a particular profile of flat space, and that's why for these masses it's fine. If I were to do heavy states in the system, it would not be. I've never really had to use any result from ABS-CFT for what I did, but for these particular masses, it's just okay. There's another question.
Yeah, considering conformally coupled fields, I mean, for massless field, I understand because I can protect their mass by shift symmetry. But if I want to insist that, like, for all my diagrams, including loops, etc., I'm still using like the conformally coupled mode functions. Is it consistent? Like, or at some point I should start like working with the generic mass?
At some point you have to. Once you start to know. The only thing that we would say is if you were to work with the Anders theory, this looks like conformally coupled scalars and some practice in top. But those theories are really useful. If you worry about the Bayesian variance of the top case, except for something like symmetric spectrum, you have to start renormalizing the area. This is a general issue with whenever the grams change. Many times we like talking about integrals, but we at some point should address what happens when we take renormalization of subgroups.